All right, this lecture is really fun, at least if I do it right. We'll talk about two combinatorial problems, vertex cover and matching. So we'll do graph algorithms for our last lecture, which always makes for the best pictures. Okay, so let me just go ahead and introduce the problems. So first one is called a vertex cover. So all of our problems will just be an undirected graph today. So in vertex cover, I give you a graph like that, and a vertex cover is a set of vertices that includes at least one endpoint from every edge. I think we looked at this just for bipartite graphs earlier when talking about flows, and now we're going to do general graphs, so not necessarily bipartite. Okay, so like here's a graph, and I guess I don't know, maybe this is too big to try to guess, but the goal is to choose a minimum number of vertices so that every edge has at least one endpoint in it. So I guess I can give you guys a chance to stare and see how small of a set you can get. I don't know if it's too big a graph to do in your head. Uh, I'll also give you a chance to play with the definition. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 20 total vertices. Can anyone do better than 20? Okay, maybe this is not so great. All right. So here, I guess, is the solution with, it's so hard to count. 6, 7, 8, 9, 10, 11, 12, maybe around 13 vertices. But hopefully, if we look at every edge, we'll see that for every edge, at least one of the two endpoints is circled. Okay, so that's the point. I want to take as few vertices as possible, but cover all the edges. Okay. All right, so I guess yeah, I guess here's maybe two more extreme examples. So a star is an example where a vertex cover is really small compared to the entire graph. A star being that graph on the right. So the basic goal is to get the minimum cardinality vertex cover. The decision version of the problem is like I also give you a cardinality k and say, oh, can you find a vertex cover of size k or less? And that turns it into a yes/no question. Okay, so that's one of the two questions we'll look at today. Okay. All right. So one basic point to point out is that you can have a minimal vertex cover and a minimum vertex cover. So minimal means I have a set of vertices and I can't remove any one of them without ruining the whole vertex cover part of it. And minimum means it's a vertex cover and it's truly the smallest. Okay, so this was like, for example, a question that came up when we talked about like spanning trees and stuff like that before, where we worked really hard to show that minimal is equal to minimum, which then allowed us to do like simple greedy algorithms and stuff like that. But that's not the case for this problem. So on the left, I have a minimal vertex cover, right? Just three vertices. If I remove any one of them, one of those edges will not be covered anymore, right? So I can't remove anyone. On the other hand, there's a better solution where I only take two of them. And I think we're all comfortable declaring that to be the true minimum. I mean, I don't think you can do better than two on this simple graph. Okay, so something to keep in mind. This is another problem where minimal is not equal to minimum, so maybe it's not as easy as something like spanning trees. I guess here's another example where that's maybe more exaggerated. So on this star graph, there's actually a very big vertex cover that's still minimal, whereas the minimum is one, right? So actually here, the difference between minimal and minimum is also essentially unbounded. Like minimal can be arbitrarily big compared to minimum. So I don't know, just some preliminary observations. Okay, the other problem we'll talk about, which we've talked about for bipartite graphs before, is matching. Okay, so we did this for bipartite graphs, but again, the goal is to take a subset of edges so that no two of them are meeting at any endpoint, right? So they're all independent. They all have different endpoints from each other. Before we only looked at bipartite graphs, which had a left and right, in which case like many assignment problems look like a bipartite matching problem. But what makes this interesting is we're looking at just a general graph now. Okay? So we're trying to do matchings in a general graph. So I guess this graph is too big to just stare at. So I guess here is an example of a matching that I picked out ahead of time, which has I can't count, 1, 2, 3, 4, 5, 6, 7, 8, 9. I guess 9 edges in it. Um, but the key point is that all these edges highlighted in purple, you can see that their endpoints are different from each other. And the goal is to try to get as many as possible. Can anyone improve this solution? Like maybe swap out one edge for two? I'm not sure actually. Yeah, does anyone see a way to do better? Yeah? Oh, how? Okay, which one should I swap out? Middle, but like here? Okay. Okay, so this I'm going to make into light blue. Oops. Okay. Rightmost. Oh, okay. Okay, so we'll take this one like that. The leftmost purple edge, this one. Okay, so I'll make this blue. Okay. All right. And then you have the two pair. Okay, one second. Help me out here. Uh, yeah. Okay, four vertices that are not matched. Okay, one, two, three, four. These are the four vertices? Okay, now I see what you're saying. Okay. Oops. Okay, so we have improved our solution from 9 to 10, which is great. Now all the vertices are matched, I think, right? Okay, so this is also optimal because every vertex is the endpoint to one of our purple edges. So I don't think we can squeeze them anymore. Okay, great. Isn't graph algorithms fun? Okay. All right. Okay, so you get the idea though. Uh, my struggles to find that suggest that this is a non-trivial problem. Like you have to really stare at it, and this is only like 20 vertices, right? This is like supposed to be very easy, and it gives me a tough time. Okay. All right. So again, the problem is, oh, to find a maximum cardinality matching, or I give you some target value k and say, oh, get a matching of size k, or is there a matching of size k? That turns it into a yes/no question. All right. Uh, just the same observations as before. I mean, it's always good to double check if maximal is equal to maximum, because then you'd have an easy algorithm, because usually getting something maximal is easy. However, the same example will show you maximal is not equal to maximum. So on the left, I've taken two edges. I can't add any more edges to it directly, right? But clearly there's a better solution of size 3 on the right. Okay. So maximal is not equal to maximum for this problem. Always good to check. Um, Here, I guess, is a 16 vertex example. And I think, I think I set this up to see if you guys can spot. I was going to ask you guys, what's the biggest matching in this graph? Yeah, Daniel. Okay, eight. Okay, sure. what is it? Okay, I think you might have seen this last year. But anyway, so I planted like a relatively simple looking match. I think what I did was I drew the matching first and then I drew a bunch of other edges on top. But anyway, so there would be a complete matching. And whenever you have a matching that covers all the vertices, that's sometimes called a perfect matching. I mean, for those who are keeping score at home. Okay. All right. Okay. So this problem is another example of a theme from earlier, which is this idea of packing and covering duality. So I can think of matching as trying to take a lot of edges, right, and pack them in, but they all conflict at endpoints, right? I'm packing the edges into the endpoints. I'm only allowed to take one edge per endpoint. Okay. So I can think of that packing problem, trying to take as many as possible, the edges being packed into vertices, and the opposite, when the vertices cover the edges, then you get the minimum vertex cover problem, right? So for every edge, I want to pick at least one of the two endpoints. Okay, so these are dual problems to each other, just like packing edges and cuts. Okay. So, okay, so that means you automatically get this for free. I'll do the calculations anyway, but this is always true of these packing and covering kind of things, that the maximum matching or the size of any matching is at most the size of any vertex cover, and in particular the minimum vertex cover. Okay, and so the proof is again, it's going to look a lot like the same proof we did when we tried to show that any path packing is at most the size of any ST cut. So let's suppose I have some matching M and I have some vertex cover S, right? And then we start stringing together some simple observations, starting with okay. So since S is a vertex cover, every edge has at least one vertex in S, right? On the other hand, those choices of vertices, each edge getting mapped to one vertex in S, they must be disjoint because the edges are vertex, the endpoints are disjoint. Okay, so the endpoints of edges in M are disjoint. So when I'm mapping those edges into mapping, when I'm mapping the edges into matching to vertices in the vertex cover, I'm mapping from an edge to a different vertex, to a different vertex, to a different vertex. So you put that all together and you conclude, okay, I'm able to kind of do an injection from edges into vertex cover. So that means the number of edges in my matching is at most the size of the vertex cover. Okay. All right, so nothing too special. Okay. Now the question is, what about the opposite direction, and possibly are they even equal? Right. So when we did ST flow and ST cuts, we were able to get the one direction really easily, where we should, okay, any path packing is at most the size of any ST cut. And that came from a relatively simple argument. And then we spent the remaining 80% of the class trying to show the opposite direction, and in fact show that they're equal, right? And that was quite an accomplishment. We had to use a pretty elaborate algorithm, the Ford-Fulkerson algorithm, to get there, right? Was this clever residual graph idea. So we're asking the same question here. Does the maximum matching equal the minimum vertex cover? Right? Does anyone have any ideas? Yeah. Okay. Here's a triangle. All right. Now, what's the size of any matching in this graph? How'd you get two? Oh, okay. So you can only take one edge, right? Because then there's only one vertex left over. So you can only take one edge in any matching. On the other hand, how many vertices are at least how many vertices are in any vertex cover? Yeah, so like one is not enough because there's still that remaining side from whatever vertex. The opposite side from whatever vertex you picked is not being covered. So you'll have to take at least two, right? So, okay, so here's a simple example where it's definitely not equal. Okay, all right, so we're not going to get the exact same thing as ST flow and ST cut. So it's already different. Even though this also seems like a simple problem, maybe simpler than ST flow and ST cut, it's already looking a little bit different. Oh, okay, so same example as what I had in mind. Okay. All right, so with all those preliminary observations, I want to take one last poll for this class. Actually, you guys could also do a survey for the class, I guess. That's the other poll if you want to. Anyway, okay, so I'm going to ask you guys if you think for each of these problems, whether it'll turn out to be in polynomial time or it'll be NP hard. Okay, so, oh, I guess for one last time, we need to figure out who's not going to vote. Okay, so yeah, you have to either vote easy, hard, or decide now you're not going to vote. Okay, so who's not voting? Doubt it, but okay. All right. Okay, so vertex cover. Who thinks that we'll be able to get a polynomial time algorithm for the minimum vertex cover? Okay. And who thinks then it will be NP hard? Okay, I would say. Okay. All right. Now, how about the matching problem? Matching in a general graph. Who thinks we'll get a polynomial time algorithm? Okay. And then who thinks it'll be NP hard? Okay. So most of us think um, that both of them will be NP hard, although we had a couple people thinking we can do matchings um, and not the other. Um, okay. Okay. One thing kind of odd for those who voted in this category is that here we have, vertex cover and matchings are dual problems, right? They feel like opposite sides of the same coin, but these two people thought that dual problems could have a different behavior, right? Where one side is hard and the other side has a polynomial time algorithm. So that's bold. Okay. All right. Okay, so you were almost all right about minimum vertex cover, maybe because I listed this in the MP hard problems on the midterm. But okay, but here's a simple we're gonna do a reduction from independent set. Okay, so let's take an instance of the independent set problem on one of these graphs on the left, and in yellow I've circled an independent set in yellow. Okay, and I want you to draw your attention to the vertices that were left out of the independent set. Okay, so uh, these are blue, the teal colored vertices. Okay. Um, what is conspicuous, or what's something interesting about the vertices colored in blue on the right? Oh, they're a vertex cover, right? So why? So is that always true? Is it always true that the opposite of an independent set is a vertex cover? Yeah, but why? Or do you have a simple explanation? All right, let me try giving this explanation. So let's take an arbitrary edge like this, right? And okay, if the only way that we don't take one of the endpoints is if somehow the independent set took both of these endpoints, right? But that can't happen in independent set because independent set they can't be connected by any edge. So I have to leave out at least one of the endpoints of any single edge, and that'll guarantee a vertex cover on the opposite side. Okay. Conversely, for any vertex cover, you have to take at least one of these two endpoints. So then on the opposite, you can only take at most one of the two endpoints in your independent set. So in fact, yeah, so an independent set is always complementary to a vertex cover. Okay, so, right. So if you can figure out the minimum size vertex cover, then you can figure out the maximum size independent set just by looking at the opposite set of vertices. Okay, and vice versa. So, okay, so vertex cover does turn out to be NP hard, because it turns out to roughly be independent set. Why did I have that twice? Okay. All right, let's go to the second question. Is maximum matching NP hard? And so I've left some space to ask you guys. Well, I guess yeah. Who wants to try to argue why it might be NP hard, or even at a high level, or like what their thought process was? And I also left some space for the two people who thought there might be a polynomial time algorithm. So what are some arguments to try to argue it's either that it's hard or easy, or why did you think it might be hard or easy? Doesn't have to be a great reason, but most of you argued hard, so you must have like come to a consensus for some reason. Yeah. Okay. Oh, that's okay. That's a good reason. Yeah, kind of similar to independent set because it's sort of like an independent set of edges in a way, right? There are edges that don't kind of touch each other. I think that's a great reason. You might suspect that we can reduce from independent set to matching because there's some kind of disjointness involved. Okay. Anything else? Here, I'll supply one reason that we showed earlier that we showed that maximal is not equal to maximum, which seems like a bad sign. I mean, if it was equal, then it would probably be easy. Any other peer pressure, maybe? I don't know. Bad vibes was once suggested in an earlier lecture. Okay. Does anyone want to argue why it might be easy, or we might have a polynomial time algorithm? Yeah. Okay, so let me explain. There's a different problem. So Hamiltonian path, you want to visit every vertex exactly once. And there's something else called like an Euler cycle. It's a cycle which visits every edge exactly once, right? That's what you have in mind. So this whole like I guess yeah, let me try to articulate. Okay, so pro easy, which is really like I guess anti hard or something. But uh, Euler cycle versus Hamiltonian path is an example where this one is easy in the sense there is a polynomial time algorithm. And this one, of course, we know is hard. It's like our favorite hard problem. At least it's my favorite on the exercises. And this is sort of like, visiting every edge exactly once, and this is visiting every vertex exactly once. So maybe there's something about edges that could make life easier, right? So it's not automatic that transferring the vertex version of the problem to the edge version of the problem, so loosely speaking, retains the same complexity. I guess is this would be a counterexample too. Okay, that's an interesting thought. Any other fun ideas? Okay, I'll give another one. Bipartite matching is easy, right? That seems kind of similar, and that we know how to do, right? So how different can general graphs really be is also maybe another way to frame the question. Should we expect different behavior going from a bipartite to general? On the other hand, we could do vertex cover on bipartite graphs, right? That turned out to be an ST cut problem, if you remember, as one of the applications. And here we already know that vertex cover is hard on general graphs, so okay, maybe there is a difference. Any other? Yeah. 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 Okay. Okay. Certainly this it certainly implies that the size of matching is smaller than the size of vertex cover. Okay, but okay, to you it feels looser, the idea that okay, there may be some vertices that aren't participating at all because you don't take any edge that uses. Okay, so I guess I'll write that as, I don't know, feels easier than vertex cover. Okay. But significantly enough that, for example, in your case, you felt differently about the two problems, which is interesting, right? Okay. All right. What else did I prepare ahead of time? Uh, oh, for some reason I wrote that finding a maximal matching is relatively easy. I could just keep adding edges, even though we know that maximal is not equal to maximum. But I guess I thought that was a good reason at the time. Okay. Oh, and then here's maybe the obvious. The obvious thing is just that the dual problem is hard, and you know. Okay. All right. All right. So much for that. What's the point of this slide? Okay. All right. So in that example we did earlier, here on the left, I have an example of a maximal matching, um, and a maximum matching, that you guys already saw before. Okay. And I'm going to take this, I'm going to, what was I trying to, okay. Now in general, if I have a maximal matching and a maximum matching, then of course the maximum matching has more edges than the maximal, or at least as many edges as the maximal. This is just a definition of the word maximum, right? So that's not too interesting. So for the next part of the discussion, I want to ask about the opposite direction, right? Can I argue that any maximal matching has some cardinality somehow related to the size of any maximal matching? For example, can I argue that, I don't know, any maximal matching has at least square root of any maximum matching or something like that, right? Or maybe any maximum matching divided by 100. And other examples include, I guess, log. But is there any opposite direction? So clearly maximal is less than equal to maximum. But can I argue that maximum is less than equal to 100 times maximal or something like that? Is there anything to bound the opposite direction? We already know it's not equal, right? We had some simple examples like the 5 edges and it was like the 3 in the middle or the 2. Anyway. Okay. All right. So now, okay. So let me take that maximal matching and maximum matching from before and throw them on top of each other. Okay. And then all the other edges are kind of grayed out. Okay. Uh, and just for sake of conversation, I'm going to assume that these two edge sets are disjoint. If they did have common edges, we can just throw them out, as kind of part of the rest of the graph. Okay. All right, so let's just look at the union of a maximal matching and a maximum matching. That's what I have in this picture here. So blue is a maximal matching in that original graph, and B in red is that maximum matching. So, okay. What? Okay. Oh, okay. So what I want to point out about this graph is that every vertex has degree at most 2, right? Because each vertex can only be incident to one edge from one matching and one edge from the other, because a matching can only have one edge incident to each vertex. Okay. So that means that actually this graph here, which might look kind of complicated, actually has a pretty simple underlying structure, and it can actually be kind of decomposed into a very simple kind of graph. So, does anyone want to take a stab at, like, what happens when a graph, the degree is 2, at most 2? It's not necessarily a tree, actually. Can anyone think of a graph that's not a tree but has degree 2? A cycle. So you can have cycles. Also, trees often have degree at least 3, at least interesting trees. Okay, so as soon as you know it has degree 2, you know that the graph is actually going to decompose into disjoint cycles and paths, right? So let me give you an example. If I start here, this is a vertex is degree 1, and I just follow, right? Oh, degree 2, so there's only one edge leaving. And degree 2, there's only one edge leaving. So I'm gradually tracing a path, right? And there's no degrees of freedom. I'm just following the only edge I could follow. And so that's one big long path. And actually, these edges are completely disjoint from any other edge. Okay. Another example, if I like start here and I start going around, right? And again, these are degree 2, so I don't have any choice. I'm just following the only edges I can, right? And when I terminate, I end up with a cycle. Okay, so once you have degree 2, you know it's going to break up into paths and cycles. Okay, so, right, here's that path, kind of highlighted more cleanly, and here is that cycle. Okay. All right, so, and of course, these paths and cycles have to alternate between the two matchings, right? Because you can't have two edges in a row from the same matching, because that would give two edges incident to the same vertex. Okay, so remember, there's still the high level goal is to maybe see if I can argue that maximum matching is at most 100 times maximal or something, right? That's the goal. So we're going to look at these two cases separately. Okay. All right. So in a cycle, right? First, it has to be an even cycle. It's going red, blue, red, blue, red, blue, right? And so since it's alternating between two colors, it has to be an even number of edges. And half of them are red and half of them are blue. So in any of these cycles, there's the same number of edges from the maximal matching and the maximum matching. Okay, so when I'm comparing their cardinalities, we're always tied on any cycle. Okay. All right. How about a path? Okay. So again, remember that everything decomposes into path and cycle. So here I'm just highlighting one of those paths. And it's alternating red, blue, red, blue, red, blue, red, blue, red, blue. Okay. So first I want to argue that the number of edges in the maximum matching has to be at least the number of edges in the maximal matching. Okay. Yeah, so actually, like take this from the standpoint of the blue matching. Okay. In the blue matching, I can actually take out all three of those blue edges and put in all four of those red edges and improve the size of the matching. Because there's no other edges that are incident to these, right? Because this is like a maximal path out of the union of the maximum. Okay? Okay, that's coming up next. Okay. So in one direction, maximum has to be at least maximal, because otherwise, if there was more blue edges than red, then I could exchange the red for the blue and improve the maximum matching. Right? So in this example, from the blue standpoint, I can replace the blue with a red and improve the blue matching. Okay? So these alternating paths actually give me sort of something like an augmenting path, similar to what we once saw with flow. Okay. Okay, what about this opposite direction? So, okay. Is there anything in the opposite direction? Can I argue that any maximal matching in the path, has at least, can I say that blue has at least red divided by 10 or something, where blue is the edges from the maximal matching, red is the edges from the maximum matching? So, sorry? Okay, so we can argue it's actually at most one, right? Because you're going red, blue, red, blue, red, blue, red, blue, or something. And so in the worst case, you go red, blue, red, or something, and you start and end at red, but then there's still almost as many blue edges except for -1. Okay. Um, what's the smallest example? So I still want to get a multiplicative factor. So additive 1 is correct. Now we just want to translate that into some multiplicative thing. So what would be like the most extreme case? Okay, so I think, or let me get to the point. So the, the worst case is just three edges because that's the smallest possible one. Where it just goes red, blue, red. There's one more red edge than blue, okay? But it does represent one half of the red edges. Okay, so if it was longer, if it was like 5, and went red, blue, red, blue, red, the score would be like 3-2. So 2 would be like at least 2/3 of 3 instead of one half of 2. So the worst multiplicative factor you'll get is one half. Okay, so it's at least one half. So -1 corresponds to one half because the worst case is I only have 3 edges like this. Okay. All right. So what does that mean? So for any maximal matching and any maximum matching, I can break it up into a bunch of cycles and paths, right? On the cycles, they're tied. Same number of red as blue. And on any one of these paths, even though red is always at least as big as blue, blue is at least one half of red. So we conclude that blue is always at least one half of red in general. They're tied on the cycles, and it's at most one half on the paths. Add them all up, the worst is one half. Okay? So we actually have shown that although a maximal matching is not necessarily a maximum matching, it's always within a factor of 2. So you just wanted a 2 approximation, then just adding as many edges as you can until you get a maximal matching will get you a 2 approximation. Okay. Okay. All right. Okay, so you can like maybe throw that into a pro easy argument because at least we have a nice easy 2 approximation, which seems better than nothing. Okay. Yeah. Yeah. Okay. All right. Okay, so we've just basically done some preliminary observations about matchings. Let's now take a slightly different perspective. Okay. So, okay, so so remember this simple example that broke up into paths and cycles, and you can trace the path, something like this. Okay, and we showed that on cycles they're equal, on paths. Okay. All right. So just to remind us that the reason why on any path a maximum matching has at least as many edges as any maximal is because if it was smaller, I could have improved the solution by swapping the red for the blue. Okay, that's what we went over. Okay, so this idea of swapping edges along a path, an edge I don't use, edge I use, edge I don't use, edge I use, edge I don't use, and swapping out the unused for the used, and thus increasing the size of your matching by 1. That's what we call an augmenting path, the same terminology we used for flow when we found the path to route 1 unit of flow from S to T. Okay, so here's like a simple example. So let's say that these red edges are edges that are matching. Okay, so we've built up a maximal matching in this simple example, right? And so in this simple example, the two endpoints, they're not matched. So there's some terminology for that. We might call them free. Okay, so a free vertex is a vertex that's not currently matched by our matching. Okay, so those opposite endpoints, there's no red edge incident to them. We're not using them. But maybe we can try to find a path where I start here, right? And here's an unused edge, a used edge, unused edge, used edge, unused edge, and I get to another free vertex, right? Where I'm alternating unused, used, unused, used, right? And then I can completely swap them, right? So I would, if I instead took these 3 edges where I exchanged the unused edges for the used edges, I've now increased the size of my matching by 1. Okay, is there anything down here? No. Okay, so that suggests some kind of algorithm where I just maybe start with an empty matching. So I start with a graph, right, with all the edges and an empty matching, and I start adding edges as much as I can, and until I get stuck. And then from there, I might try to find the path where first I pick out some vertex that's not matched right now, somewhere in the graph, and I try to find one of these augmenting paths that alternate from an unused edge to a used edge. Unused, use, unused, use, unused. And then maybe this last vertex also is not matched yet, right? And then I can, swap all the black edges with the red edges in this picture, and my matching will go up in size by 1. Okay, so that seems like a potential algorithm where I keep trying to find these alternating, augmenting paths where I can exchange all the edges along the path, increase the size of the matching by 1. Okay. All right. So that seems like an algorithm or an algorithm starting to come together. Okay. Right. Okay. So there's a simple example. There's the path. I swap them out. 2 edges have been replaced by 3. Okay. Now, let's say I had such an algorithm. There's still some question about how to find an augmenting path and stuff like that. But in principle, suppose such an algorithm was okay. And suppose somehow, your algorithm is keep trying to find these augmenting paths, and maybe it does increase the size of matching until it reaches a point where there's no more augmenting paths. What happens when there's no augmenting path? Yeah, from one free vertex to another. So there could still be lots of free vertices out there. There's just no way to get from one free vertex to another along one of these alternating paths. Well, oh, yeah. Yeah, so let's try to argue that in that case, we'd have a maximum matching, right? So what we do is now we imagine we're that maximum matching. We're blue, right? We might not be best yet, right? And we can presuppose some maximum matching out there. We don't know it, but for the sake of analysis, imagine, fix a maximum matching in red, right? So I know that if I put those on top of each other like we did before and broke it down into cycles and paths, okay, we already know we tie on all the cycles, right? And for paths, I know I'm within a factor of 2, but actually if I'm blue and red is the true maximum, and if it went like red, if it went blue, red, sorry, if it went red, blue, red or something, where there's more red edges than blue, that would be an augmenting path, right? But there are no augmenting paths. So on all these paths, it must go like red, blue, and it just stops. Okay. In other words, we're also tying on all the paths. Okay. So if I had combined the two and overlaid them, I know that we're automatically tied on the path on the cycles, and I have to be tied on the paths too because if I was losing by 1, that would indicate an augmenting path. Okay. But there are none. Okay. So if there is no augmenting path, then we'll kind of win or tie in that comparison game compared to any other matching. So we conclude that we have a maximum matching. Okay. All right. So at least the high-level pieces of an algorithm are there. Given the graph, I'll start with an empty matching, and I'll repeatedly, until I can't find any more augmenting path, look for an augmenting path from one free vertex to another. And if I find one, exchange along that path and increase my matching by 1 total edge. Right? So each time I do this, red, blue, red kind of thing, and I can swap the red for the blue, and I've gone up by 1 edge. Okay? All right, so this seems like a reasonable algorithm, and at some level, this algorithm sort of works. We know that if we find no augmenting path, we now know it's an optimum solution. Right? But what's maybe one missing detail? One of these steps are actually harder than it looks. Yeah. Yeah, finding an augmenting path. So how do we find one? So okay, let me look at a simple case. Suppose I wanted to find an augmenting path in a bipartite graph. Okay. So here we have the current matching is in red and the rest of the graph is in blue. So here are two free vertices. Okay. And the question is, can I find an augmenting path from one purple to another? Or can you guys find it? Let me know when you do, and then we'll trace it. Yeah, okay, so I'll start here. Should I go like up or down? Okay, I'll go like this. And then there's only one choice on the way back because it's a matched edge. And I guess here I only have one choice. And now what? Take the lower. Okay, and then? Okay. Are you guys, is that an augmenting path? What went wrong? Yeah, why? Ah, we took consecutive blues. We have to go blue, red, blue, red, blue. Okay, so that means if we went here, we would have to go this way. Sorry, that wasn't a great squiggly line. Not that any of them are particularly great. Okay, and now, anyone want to keep going? The top one or middle one? Middle. Okay, and then we have to take red. There, that would be an augmenting path if you can make out what's going on in the purple lines. But we did go blue, red, blue, red, blue, red, blue, and go from one free vertex to another. Okay. All right, so great. The question, how do I automate this search? I mean, we did a simple example together, but how can I do this automatically? I would write an algorithm to find one of these augmenting paths from a free vertex to another, or declare that there is none. Yeah. Okay, I can try DFS or something. We can try breadth first search or DFS. But one thing we have to be careful about is that remember in our first attempt we went on three straight blue edges, right? So if I just apply DFS or BFS to this graph, it's not necessarily obeying the blue red rule. How can I encode that? Is there a trick I can do beyond trying to reinvent BFS and doing some awfully complicated thing? Yeah. But this vertex also had both blue and red, for example, the one that gave us trouble. The problem is that when we visited it, we went blue, blue. Okay, but is there some small chance that our algorithm will kind of visit both copies of the vertex? If we're not careful at least. I'm thinking of a simpler trick in any case. Well, maybe I'll point out that every time I took a blue edge, which direction was I going? Yeah, from left to right, like that first edge, right? And every time I took a red edge, which direction was I going? So we went, from your point of view, blue, red, blue, red, blue, red. So they're always going, red was always going in the opposite direction whenever I took a red edge. I was going from right to left. All right, that was my hint. Yeah. Okay, yeah. So we can turn it into a directed graph where the unmatched edges I'll have going from left to right, and the matched edges I'll have going from right to left. Okay. And then I guess what I would do is maybe I'll make a, if there was more than one free vertex, I would have an extra start vertex and an extra end vertex and connect all those free vertices so that it can choose roughly which free vertex to start at. Because I'm happy to start at any free and end at any free, right? Okay. All right, so you can do something like this, right? And now I just find a path from start to finish. And if it finds one, that'll give me my augmenting path. If it doesn't, then there is no augmenting path. All right. Does this seem familiar, what we just did? Does this remind anyone of anything? Max flow, right? We have a flow algorithm, right? This is actually looks a lot like how we set up our flow algorithm for bipartite matching, right? I put a starting vertex on the left and connected it to everything, a source on the left and connected to everything, and I had a sink on the right and connected everything. And then every time I added one unit of flow, I add the reverse edge back to the graph, right? And that's exactly what's happening. The edges with flow are the edges in our matching, right? And whenever I take an edge in a matching or route one unit of flow, I put the opposite direction back in. So actually, this trick is exactly what Ford-Fulkerson would do when we apply it to bipartite matching. All right, all right. Okay, how about general graphs, right? All right, so let's say here's like a free vertex, right? And I want to find some kind of augmenting path, right? So we can try doing something similar where I alternate between blue and red and just use some kind of depth first search or something, right? Like you can go like this, so blue first, and then I have to go red, right? And then maybe I go blue, and then I go red, right? And then I go blue. Okay, something weird has happened. Um, actually, yeah, let me explain. So, okay, this was the example, right? I went blue, red, and blue. And what just happened? I suddenly like revisited the same vertex, right? Like a random, a cycle has suddenly appeared in my search. That could never happen in a bipartite case because blue was one way and red was the other. Okay. But here I suddenly found a cycle, right? And for some reason, yeah. Okay. So when we do an augmenting search with a red blue kind of graph, you can get something weird like an odd cycle. Okay, which wouldn't normally happen. Okay. Okay. So, uh, right. So in general, right, if I did one of these searches, right, I might conclude uh, that there is no augmenting path, but the real issue is that I can get stuck on these odd alternating cycles, sometimes called blossoms. Okay, this can't happen in a bipartite graph because all the cycles have to be even. Okay? Um, but here we can get stuck. Okay, so it's not obvious how to add directions because there's no left and right, right? We can't just add directions like we did with the bipartite graph. And in general, searching for these augmenting paths, I can get stuck um, at these odd cycles. Okay. All right, so we have some terminology for this. I mean, for some reason, someone invented this. Okay, so when this arises in an augmenting path algorithm for general matchings, it's sometimes called a flower. And the terminology is like, okay, so you started a free vertex, And this part here is like, maybe I'll do a different color. This part here is called, I guess, the stem or the base of the flower. And for whatever reason, this odd cycle that occurred, which in hindsight I could have traversed in either direction, is called a blossom. Okay. So these blossoms give me a lot of trouble in an augmenting path algorithm. Okay. All right. So okay. Okay. So now, okay. So here's right. Right. Okay. So here's what we want. Okay. So let me give an example of why this can be problematic. So let me simplify this graph a little bit. Um, okay. All right. So in general, in this graph, um, there is an example, an augmenting path. I don't know if the font is too small, but here I'm going on red, blue, red, blue, red, blue, red, right? That would be an augmenting path. Okay. In this graph, it's alternating red, blue, red, blue. The only point you have to be careful is right here. Okay, that first edge leading the blossom was blue. Okay. But if you had gone the opposite direction around this blossom, okay, so if you had gone like this, right, and you reached this point here, right, you've just taken a blue edge. And so you're not allowed to go that way, right? You can't go that way because that would go blue, blue, right? And so the algorithm, if we're just doing depth first search, except somehow we've coded in you have to go red, blue, we just keep going this way, and then it'll die, and it'll say, okay, there's no augmenting path. Because it went the wrong way around the blossom, right? So these blossoms are really problematic. Now this might be simple. You might think, oh, just go the other way around the blossom. Okay, there could be tons of blossoms, right? And you don't know, like, even when you're entering something that you're in a blossom until it's too late and stuff like that. So it's hard to systematically be like, oh, I've enumerated all the blossoms. There can be arbitrarily many, and we're going to try all the directions in all the blossoms and stuff like that. That wouldn't actually work. So, okay. Okay, so all right, so that's the kind of problem that can happen, right? I'm walking around, I'm doing some depth first search where I'm going red, blue, I'm following those rules, but I run into an odd cycle, right? So from here I can't really, so by the time I get to this point, I've already entered along this red edge. So I've already used that red edge. So by the time I get to this vertex, I can't leave anymore. There's no other red edges I can take, right? And so the search would just die. Okay, so the question now is what the hell am I going to do with these blossoms? Right? This is the only reason why we almost have an algorithm. If I can find augmenting paths correctly, we have an algorithm for this matching problem, which most of us thought was going to be MP hard. The only thing standing in our way right now is these annoying odd cycles, odd length cycles. The question is how? How do I address blossoms? Yeah. Okay, so here's what we're going to do. And this is the more surprising steps. Let me redraw this a little bit. So you go there, and then this is the blossom on the inside. Okay, so here's what we're going to do. We're going to take this set of edges and corresponding vertices. Okay, and I'm going to shrink it. Okay, I'm going to shrink it to like a single vertex. Okay, and then that's attached to all these. things. Okay, so that's what we're going to do. If on my search I run into an odd cycle, I'm going to collapse the odd cycle to a single vertex, and then whatever was hanging off any of those vertices in the cycle is just going to get reattached to this new super vertex that represents the old blossom, right? This is a freaky step. It should be probably the most surprising thing we've done in the class, at least algorithmically. Okay, we found the blossom and we decided we're going to shrink it. Okay, all right, and now, so now I have a graph where I took the cycle and it's a little bit smaller than last time, and I'm going to try to do my search again. So I'm going to search like this, right? I come in on a red edge, right? And now I can leave off of any blue edge. So I don't know, I could go like this or something. Okay? So in that shrunken graph, I find an augmenting path, right? Okay. But now, okay, so here's a different, I guess, example. Okay. Now, look, I want to be able to turn this into an augmenting path in the original graph. Right? That's what we're really looking for. We're looking for an augmenting path. In the original graph, I found an augmenting path in this graph where I conveniently shrunk a blossom to a single vertex. Yeah. Oh, why did the path always start at an edge where the first one is blue? Oh, oh yeah, so that's an interesting question. So look at this. By coincidence, right? When I found this blossom, here it's a little hard to see, so I'll erase this. So if you look carefully, we have one red edge that's going into the blossom. And at least by coincidence, all the other edges that are leaving it happen to be blue. Right? That edge is blue and that edge is blue. Is that a coincidence or is that always true? Okay. So if I was going to put a red edge, attached anywhere, right? Where would I put it? If I was going to attach a red edge, where would I put it? Remember, red edges are matching. Ah, okay. So the blossom, right? It's alternating everywhere except at that base point of the blossom where the stem met the blossom. You had two blue edges in a row. Okay, so in the odd cycle, it's generally going red, blue, red, blue, red, blue, except at one point it goes blue, blue. Two unmatched edges in a row. That's the only point where we can enter on a red edge. So that's a good observation. Ah, okay, yeah, so maybe it's actually good to point out. So when I did shrink this, I still had a matching, right? Because I only had one red edge going into that super vertex and everything else was blue. So by shrinking those vertices down, I didn't accidentally bring two red edges together. That's actually a very good observation. Good, I probably should have mentioned that. Okay. All right, so let's say I find an augmenting path like this. Okay. Now, right, so when I expand it back out, those are sort of the edges that I had previously selected, right? Now, what's great, right, is that if I look at like where I leave the blossom, right, I could have come in from this direction or that direction potentially, right? But one of these directions, the one going down, is impossible because then you would go blue, blue. But the other direction, you would come out of red, right? So the point is that there's two different ways around this blossom to connect my path. And one of the ways is always going to help us, right? Whichever way ends on red so that I could take that blue edge out will let us get out of the blossom. So I might have to spend a little time figuring out which way to go around, but that's not so hard. And in this case, I can go this way and I can get out of the blossom, right? So I can actually shrink a blossom, find a new augmenting path, or maybe keep shrinking more blossoms. But once I find an augmenting path with various blossoms shrunk, I can actually expand them back out, expand them back out, expand it back out. And every time I do, it's going in, it's going out, and I just need to choose one of the two directions around the blossom to connect everything together. Okay, everything barely works. Okay, here is, I guess, another example. If I was going like this, right, and that was my augmenting path. Then when you expand it back out, based on how the edges are, you would actually go the other way around the blossom. Okay, so I go into the blossom and here I'm taking the top path and I'm going back out, right? The choice of direction depends on how do I preserve this blue, red, blue, red, blue, red, alternating colors. Okay, and always one of the two directions will work if you think about what's going on. Okay, right, so those are kind of two basic examples, but the basic idea is we find a blossom and we shrink it. If we find an augmenting path, we can start unshrinking the blossoms and reconnecting by going one way or the other around the blossom. Okay. All right. All right. So this is sort of, I think we have enough intuition where we don't have to do a formal proof. But if you have the first lemma says that if you have a matching and you find a blossom, right, and you shrink the blossom, you get the smaller graph. If you find an augmenting path in the smaller graph, you can get augmenting path in the original graph by expanding back out and choosing one of the two directions. Okay. Conversely, in your original graph, if there was an augmenting path, right, which maybe you can't find because of this blossom, right, and you shrink the graph, it'll still be an augmenting path in the shrunken graph, where the part going through the blossom will kind of collapse down together, but you'll still have an augmenting path, right? Because your goal is to say, oh, is there an augmenting path in the original graph or not? So I want to make sure that if there was an augmenting path, when I shrunk everything down, there's still an augmenting path. So yes still means yes and no still means no. So you have to double check both directions, right? I think I've drawn enough pictures so I don't have to do it too formally, but that's the idea. Okay, so that's, yeah, so you get something like this. Right, okay. Okay, I'll keep it short because we're running out of time. Okay, so I do that proof a little more slowly in the notes, but I think the gist of it is clear. So now we have an algorithm that sort of expands upon our original augmenting path algorithm. Okay, it takes this augmenting path idea, and it turns out to be hard to find augmenting path without this clever idea of if you find a blossom, shrink it. Okay, and then when you find an augmenting path in a shrunken graph, expand it back out. Okay, and that is our algorithm. Okay, this blossom idea was like very exciting because matching is a really basic problem, and it's a very kind of creative solution. It is a really simple to state problem. Okay, all right. Let's quickly do the running time. So each time I do some kind of search and I either find a blossom or a path, how long would it take to do a search? Okay, it's going to take like linear time, just doing like a breadth first search, maybe with some adjustments to make sure you go red, blue, red, blue. Okay. And how many times can I keep finding? Okay, so you might have to keep finding a lot of blossoms until you finally get a path. But how many times can we find blossoms? At most. So each time I find the blossoms, I take a bunch of vertices and turn it into one vertex. So the number of vertices goes down. So that gives us n vertices. And then what's the maximum number of like outer iterations? How many paths until I get a perfect matching? How big can a matching be? N or n over 2? because each edge uses both endpoints. The maximum number of edges in any path, okay, is n over 2. So we get an mn squared time algorithm. Okay? Of course, you have to do some careful stuff to make sure you organize your blossoms and stuff like that and collapse it carefully, but that's just kind of straightforward. All right, I want to conclude with just some historical notes because this is a historically important paper. So this is work by Jack Edmonds, same from Edmonds Karp. I think it's worth pointing out, this is from 1963. So this is 9 years before we had the theory of P versus NP, before Richard Karp had all his reductions. Maybe 8 or 7 years before also Cook-Levin theorem and stuff like that. It's 10 years before even a C programming language. So we didn't even have like a very good idea of what programs would look like, right? Like life before C is terrible, unless you're like using Lisp or something, but that's like 10 people at MIT. So like, so life before, yeah, it's not what we think of when we think of programming today. They're doing like cards and, all this terrible stuff. And so what's, obviously the algorithm is incredibly clever and fun to draw pictures and stuff like that. But it is a very interesting, so Edmonds was one of the first people to really start pushing the idea of what it means to be an efficient algorithm. So at the time, people were debating like, oh, any brute force algorithm that does the job, I'm happy with, right? And he was trying to put this idea of, no, that's not what it means to be an efficient algorithm. It's not interesting to do brute force algorithms. Okay, so, at that point, we did already have the Ford-Fulkerson algorithm that's mentioned here. Hoffman did bipartite matching, right? So we already had a bipartite matching algorithm for Ford-Fulkerson that existed. That was even like 10 years earlier than this. And he also does weighted matchings later. But he has this amazing section 2 called digression, right? And this is where I find it interesting. This is my last thought for the whole class. So I'll just read it out loud. There's an obvious finite algorithm, right? Where you just, enumerate everything. But the running time, is exponential in the size of the graph, right? So these are like relatively new phrases for the time. And it's no means obvious whether or not there exists an algorithm whose difficulty increases only algebraically with the size of the graph. Algebraically at the time meant polynomially. Okay, so this is like 50 years ago, so it's different words. And, the mathematical significance of this paper rests largely on the assumption that the two preceding sentences have mathematical meaning. So at the time, there wasn't a large emphasis, or, now we make a big difference between polynomial versus exponential, but that was still kind of up for debate at the time. Here he's talking about asymptotic estimates of the running time being theoretically important, so ignoring constants. Again, this is like still, he's not the only person saying this, but this is still relatively new. And then for practical purposes, the difference between polynomial and exponential running times is more important than the difference between finite and non-finite. Okay? And in here he asks a really important question: how good is the simplex algorithm, which we still don't have a great answer for, but he's already aware of this. So this is a pretty amazing paper. He gets n to the fourth because he's not counting it. He just says there's n squared edges, and he doesn't worry about n. Yeah, so that's something I wanted to point out. So this is also a historically very important paper because it also makes a real argument to focus on polynomial time algorithm, and it's really a highly non-trivial polynomial time algorithm. So at the point this paper comes out, there is some excitement. If we can solve matchings with an idea as exciting or clever as blossoms, then we can maybe solve Hamiltonian path, and we can solve this, and we can solve that. And it isn't until Karp, comes around 9 years later and just kills all our dreams with all of his reductions. Okay, so this is a really important paper. It's also important in combinatorial optimization for other technical reasons, but even in the history of computer science, this is like way up there. Okay, that's the last lecture. I'll see you guys on Monday. Have fun studying all the problems.